give you a general introduction, so I don't think the first one will need 1 hour. So I will try to squeeze the 2 lectures into 1.5 hours, so we can just dismiss, okay? And in the first lecture, because it's introduction, so I don't think you need to note down something. So I switch off the lights. For this module, we have 2 lecturers and the 2 Chinese guys. I'm the second one. My name is Xiangyin Meng. Yeah, you can just call me Dr. Meng, because I think the first one is a bit difficult to you. Right? Yeah. Not monk. Meng. Yeah, okay. Or if you are from Asia, I think it's easy to you to pronounce it Xiangyin, right? But anyway, I don't mind. And here is my email address. So if you have any questions regarding this module or anything, you can just drop me an email, okay? Well, I think, have you seen the other lecture? No. Other lecture already? No? Not yet. Not yet. Okay, he's a very nice guy as well. I'm sure.
Hi, will you be putting the lecture slides on blackboards?
Of course, after my lectures. Because according to my experience, I always have some mistakes in my teaching. So I prefer uploading the materials after the lectures. Yeah. Is that okay to you?
Yes.
Yeah, that's right.
I think it's better. So, the module name is Dynamics of Offshore Installation. So we will learn something about the calculation for hydrodynamics for offshore structures like this. Probably it's for fixed structures, probably it's for the floating structures with a lot of motions. But anyway, we can just start. It's a new pointer, I don't even know how to use. Oh. Okay, so if you go to our system or go to, we have, because you are quite new to our school or to this university, right?
Yes.
Or maybe quite new to this country. Yeah. We have a system, we call that MOFs. It's a module outline form. So from this system, you can see some very basic information for different modules. Like if you have the form for this module, you can see some information like the aims of this module. And for this, we have how many points? 5 points. We have 5 aims in general to let you know what we will learn from this module. But actually the points, they were not from me, they were from Professor Long Bin, because he is the stream leader in this area in our school. And if you go to another page of this form, maybe you can see, no, I don't have them in my slides. You can see aims. You can see some outcomes, including knowledge outcome, and together with some skill outcomes. So let you know what you can learn from this module. Okay, it's quite basic. We will try to make sure we tell you everything in this slide. Okay. But anyway, after this module, you will know some basic information about how to estimate the motions of structures, or how to estimate the forces acting on the structures. It could be fixed structure, it could be a floating structure, okay? And for this module, we have, I think if I was right, we have 24 hours. and 12 hours from me, 12 hours from Dr. Wen Xuan. And the exam will be just after Christmas holiday, right? I think I was right. So I will do the, that's why you haven't seen Dr. Wen Xuan, because I do this first. I have 6 weeks to give you 12 hours lectures, but the last one will be a review. So we have 10 hours to do some real lectures, okay? And the first one, I'm doing the first one. I will give you an overview in this area or in this module, and we will know something about wind. We will start with wind, okay? And about the exam, we don't have any presentations for this one, and we have only 4 questions in your exam paper, and you have 2 hours to answer all the questions. Usually we have 4 questions and 25 marks each. Okay. Please remember that in this module you have to answer all the questions, because in some other modules we may have a style like you have 6 questions, but probably you don't like some of them. You just need to answer 3 or 4. I can't remember, but roughly like that. It's another style. But in this one, if you drop any questions, you drop the marks.
Oh, God.
Yeah. Don't be surprised. Well, about the textbook, probably it's a bit different in England, because for example, when I was in China, we always have a textbook for any modules, and my bag is always very heavy. But in England, we usually don't have any textbooks. After the lectures, you can just go to the library or ask Google. Okay. And as you know, we have a very good library, and we have a lot of resources. So I don't think it's a problem if you don't have textbook. And they are from Professor Longbin, because I didn't change too much based on his materials, for the reason that it's my first year to teach this module. I just want to follow his style. But previously, in previous years, he showed us some reference books or some publications if you are interested for some topics. But to be honest, I really think you should search some new ones, because if you have a look, they are quite old.
Yeah.
The latest one is here, 11 years ago. So, but in this area, I have a suggestion. We have a very good handbook. The name is Handbook of Offshore Engineering. I don't know whether you have heard this. In this morning, I think I can download from our library. So if you are interested, you can download one. It's a quite good handbook. Not in very details, but in that handbook, you can find many papers like this. It's a combination of some good papers to cover different topics in the area of offshore engineering. So if you can download, I would suggest you go to library to download that book. It's quite thick one. So I think we can just start the introduction for this module or for the offshore engineering. So the first topic is about the definition of offshore structure. If you don't look at this slide, how to define the offshore structure in your mind? Probably you are from different countries and you have different definitions in your language. But after that, after thinking about it, if you look at this definition, I think it's make a lot of sense, right? Because you can see that its definition, the key point is here. If you have an offshore structure and there is no fixed access to land, we can just call it offshore structure, right? But for offshore structures, we may have different types. It could be fixed, like some rigs, and fixed on seabed. But if we go further to open sea, because the water depth is quite big, so it's not possible to build up a rig with, for example, 2,000 meters. So we use floating structures. But, sorry? In this category, we also have different things, like if you have mooring length, you don't have very, very big motion. But if you don't have mooring length, it will be drift with waves or current or wind, probably. But to control the drifted structures, sometimes we have dynamic positioning systems to control the position. So in this category, we also have 3 different things. Okay, the history of offshore structure. In this slide or in this photo, you can see some fixed structures, but as you can see, with years or with the development or with some new technologies, we can go further and further to open sea. But it's still quite old because it's just stopped at 1988. Today we can do some structures like this for nearly 500 meters, and for floating structures we are going to 3,000 meters, and in future projects it's possible for 5,000 meters. It's quite deep. Deep water production, not important. I skip this. So about the types, we know we have fixed structures, we have floating structures, but even in this category we also have different things. Like in this slide, we may have steel structures, like the first one, or we may have concrete structures, like the second one. About this one, it's quite heavy. It could be 500,000 tons, but the cost is quite low because we don't need any steel materials. We just need concrete and just put there because it's quite heavy, so it's very stable and it's okay to bad weathers. And because it's heavy, it's big, we can have some storage units, so you don't have to transport the oil immediately after production. You can just store there until some ships or some vessels come here for the transportation. Again, this board is not big enough. In steel structures, we can have 2 different types. The first one is jacket structure. Another one is jack-up structures. About jacket structure, here it is. It's designed for this location with given water depth. So after the oil and gas in this area is gone, your job is finished and you need to dismantle this structure. But you can't use it for other locations because it's just designed for this weather condition, for this location with a given water depth. But I can show you a very attractive video. for this type of structure. Okay, I got this from YouTube. It's about the installation of this jacket structure. I don't know why, but we should have some music. And sometimes in my videos you should have some presentations together, but it's a new one in 2014, and I think it was designed by a Holland company. This moment, it was just before the launch. So see, this jacket was designed just for this location, and so they just put it here. And the deck is fixed for this water depths. So after this project, it should be dismantled and take away. And I don't think it can be used for any other projects. So see that they just put this structure here, and after this, I think in June or July, they put the deck on that and to give some equipment, and then they can give production. But we know that the jacket van is not okay to use for other projects, but we also have the jack-up van. But this is not a real project. It's an animation, just so you have to work with this structure. And you can see that here is the deck, and we have 3 legs. So in this project, or in this structure, we can change the height of this deck. So it means it can be used for different locations with different water depths. Okay. So after this project, after the oil and gas in this field is gone, you can just put it away to another project with different water depths. So it's quite a smart design. Okay. So apart from the fixed structures, to open seas, we also have some floating designs or floating structures, because I think you have been in this area for at least several years, right? So I think at least you are familiar with some of them. But anyway, from shallow water to deep sea, we have different designs, and because they could be very big, and another reason is they are always far away from onshore facilities. So some of them, or most of them, like FPSO, like this bar, or like the semi-submersible, because the size could be very big, so they always have some units for storage. So you can just product the oil and gas and store on your facilities, and then maybe the vessels come here every week. They can transport the product to onshore facilities. So when we look at the structures or the projects like this, they always have different functions. And of course, for different functions and for different requirements, they have different designs. But roughly, we can put them into 3 things: productions, or 3 functions: production, storage, and export system. But for a big structure like this, usually they have the 3 functions together. It's okay to give some productions, it's okay to store the products, and of course sometimes it's okay for transportation. And I can show you a very typical working style, like we have different rigs, and we have FPSO. So for this one, it's okay for production, right? And it's okay for storage. So it's a combination of different functions. But for this one, it's for production only, and it's not okay for transportation. But some devices, like the risers, they are for transportation, and probably we have some other small shuttles just for transportation. Okay, so in a project or in a big system, we may have different things for different functions. And what is this? It's another video, but just want to show you a storage unit. Again, it's animation. So sometimes, last year in our school, they had a project for MN students, and they designed a system like this because they have onshore facilities here for processing. And they have a really big ship here for transportation, and they have something in open sea for production. But the problem is, here is a good port, but for big ships, it's not okay because the water depth is too small, too shallow, yes. So they need a station for another for another storage, like that one. So in this case, their ship could be here, somewhere with a greater water depth. It's okay, and but they can put these products here, and they just leave. So it's quite efficient, right? And then you can do some works between the processing facilities and this storage unit. Okay, so to different locations, you may have different designs. And today, we have many projects around the world. And for shallow water, you can see the yellow points or yellow areas. Roughly, it's around the Africa. It's around the North Sea. It's around the where is it? Gulf of Mexico, close to America. And for deep sea projects, we have some in Australia. We have some in South China Sea, and we also have a field very close to North Pole. Okay, don't have to remember that. And in this lecture is a general view of this area. I would like to finish with a failed project. It happened in 15 years ago. I think if I was right, this accident was close to Brazil, or maybe 100 miles to Brazil coastline. And as you can see from this photo, it's quite new, right? Because it's just after 5 or 6 years of the launch. It was launched in, I think it's according to my notes, 1995, you are right. And just after 5 years, it's gone. And now the conclusion is some designs are not very good, and there was a big accident of explosion. I think more than 10 people were killed in this accident, and after 5 days, it's gone. And today, I think it's standing on the seabed, just around here, and the water depth is about 1,200 meters. So based on our technologies today, I don't think they can take it up very soon. Maybe after another 20 years, probably. But the problem is there was some crude oil on these facilities when it was gone, and I think it's more than 1,000 tons. And it's so today it's just like a bomb to marine environment. So that's the meaning of the module like this. We need to know some more factors when we design this structure like this, and we should give we always try to give a better design for a structure like this. So to a floating structure like this one, the most important thing is fatigue and the risk assessment under different weather conditions. So that's why we focus on dynamics of offshore engineering, because it's always the most important thing, or one of the most important things. So I think I can just stop here to finish my introduction, and in next lecture we do something about wind. Okay? So I think we can have a very short break. If you don't want a break, I can just start over, and we can finish maybe after another 40 minutes. It's up to you.
That's fine. Yeah.
That's fine? I have another 4 hours to teach today, apart from this module. So I really want to go back a bit earlier. It's a dark Friday.
But it's Friday.
Yeah, it's Friday, but to me it's not a good Friday.
Could you turn the lights on, please?
Yeah, of course, because in next lecture we have some calculations.
Okay.
Yeah.
Because I cannot see what I'm writing on them.
Oh, sorry. I think I can control the lights separately, but I can't find the speech.
Whoa.
So this time you can't see this. Lecture 2. Okay, so because in this lecture we will do some calculations, so I will try to slow down until you know everything. When we talk about the dynamics, we have some factors from wind, current. Am I right?
Yeah, that's right.
Anything else? Waves? The three most important factors to a floating structure or anything else in open sea, right? The reason why I started from wind, it's because it's quite easy. Because probably you know that to do the simulations for waves, we may need many theoretical things. But about wind, you just need a speed, right? Wind speed. And of course, you need a direction. To most cases, that's it. That's enough, because in open sea you have water surface, you have a structure, and the wind in most cases is just like this with the speed. Not like waves. If we look at this structure from sky, like a god, like the god. And the waves could be wave 1, wave 2, wave 3, and of course sometimes they have different combinations, so it's quite difficult. But to wind, usually it's very easy. So we can start from here. Guide waves, guide current. Today we do wind only. So the first bullet point. It's not like waves or even regular waves. Wind and current are quite simple, right? And it's mainly based on some empirical equations. The second one, of course, even I don't say that, you know, if we have a project, here is water surface, here is the part over water surface, and here is the part underwater. The wind force is not very important just to this project, because you have a big current force underwater, and the force from wind probably is nearly zero compared to this one, or from waves. But if we have a project, like in a normal practical case, usually we have a structure with some lights, and we have deck, we have deck halls, we have some other facilities. So you see that the areas or the faces of them are quite big. So to wind, you can't ignore the force from wind, and it's quite a big part compared to the force from current or from waves. So if we have a wind here acting on this structure, we can put them into different categories. The first one is the stable part, or we can call that pressure, right? If you have, I tell you, you have a wind with 10 meters per second, and the direction is from somewhere. You can, of course, you know that the force on that is quite stable, right? Because you just calculate based on this value and based on this direction. So we can just call that pressure, and we have some empirical equations to calculate the pressure. But sometimes, and it's quite normal, because if you just stand outside or stand over sea, you can feel that the wind speed is, if you record something, it's like this. Yeah, probably you have an average value, but it's always fluctuated. So fluctuation to different parts. If for practical design, in most cases, we don't have to think about the fluctuation, because sometimes it's quite small, I mean the fluctuation part. So as long as you know this speed here, the average speed, is okay for the pressure calculation. So in most cases, it's enough. But anyway, when we talk about the wind, we need some other points to understand. The first one is, when I say average speed here, usually it's the average speed in 1 hour duration. Okay, probably in this hour you measure 3 times, 5 times, or 10 times, but anyway, it's an average value for this hour, for 1 hour. Another thing is, you may know that if we have a flow, and here is the ground, the flow speed will be something like this. Because you always have frictions from ground, right? So when we say wind speed, if you don't have any other requirements or instructions, we assume that the speed is at 10 meters over the ground, because in this part it's not the real case. And we have the exactly same thing over sea. If we assume that here is the water surface, you also have the frictions from water. So we assume that it's over 10 meters, or 10 meters over the water surface, or roughly 30 feet, 30 foot. Again, when I say the average wind speed, we can also call that the mean wind speed. If you don't have any specific definitions, it's for a 100-year return period. That's a long time. But sometimes maybe you have a definition for 50 years or 200 years. Roughly, the meaning is like this. If you design something based on the value with the confidence of 100-year return period, it's not likely happen again in this 100 years, but not a promise. Please remember that. It's a criteria, but it's not a promise. About this, we have a very silly story in China, because probably you know that we have a very good dam. We call that Three Gorges Dam, and I think it's the largest one in the world. And before they proposed this project, they want to get more money from government, and they say it's for a 1,000-year return period, and we can control the flood in downstream areas. But after they build up the dam, they think it's too risk to say something like that, and they change the presentations. They say it's it's for 500-year return period. But after we used that about 10 years ago, we found that we still have flood every 2 years in downstream areas. So they changed the presentation again. It's for 100-year return period, because they have money already, so they don't care. But anyway, from the point of view of that designer, I think it's correct, because you can say something like this, but it's not a promise. Okay? They are different. But anyway, when we say when we present a wind or the wind features in this area, we always have something like here. We call that wind rules. Many years ago, it's very simple, and just like we have some circles and we have some arrows, or we call that spokes. Am I right? Yeah. My English is not very good. But today, we also have some different colors, so we can have a wind rules like this. I don't know whether you have seen this before, but in my research I don't use wind rules. But I think it's still quite easy to understand, because you can see different directions around this circle, like the north, south, west, east, and the northeast, and the north of northeast, or something like that. And you have different spokes with different length. So according to the length, and you have different marks on the circles, you can read the percentage. Here is the probability of the wind in that direction. Okay, and because we have different colors, you just for the wind in one direction, you can also see the percentage of the winds in different speeds. So we can get some information like that: the directions, the percentage, and the different speed. And for different areas, you can have different plots like this. So, like I just said, sometimes we assume that when you say wind speed is for 1 year, 100-year return period, but sometimes it's for 50 years, 200 years, or 500 years. For 50 years, usually it's from the data, because to different areas, we always have some records for the wind speed. So 50 years, in most cases, is the reference value. Based on this reference value from your records, you can calculate the wind speed with different confidence of different 100 years. And we have estimation here. If you want to know a mean speed with n years return period, it can be calculated or estimated by this. Ln and we use the reference value at 50 years, and we can get this from some reference books for different areas. So another thing, another equation or another estimation, I shouldn't delete it. For different heights, we have a profile for wind speed. And oh, sorry, I'm wrong. Here is the height. Here is u. Much better, right? So for this profile, we also have estimation, and we need a reference value. We need a reference velocity. We need a reference height, and this one we know that if you don't have any specific instruction, it's 10 meters. Okay. And this one, if we don't have any specific requirements, it's for 50 years. So it's 50 years at 10 meters. But anyway, we can change them. So if we have something like this as a reference value, we can calculate the values at different points. Okay. That's the estimation. And again, previously we say that usually when we say mean speed, we say we measure the wind speed in 1 hour. But actually, if you measure this speed in different time periods, we may have different constants for calculations. Okay, and here is a table from somewhere, but to me it's from Professor Longbin, and I think something is wrong here. So yesterday I want to check it with Professor Longbin, but he was not in his office. So I will upload this after I can make sure it's correct. Okay, that's the reason why I don't upload this before my lectures. So for the first estimation, can you do some calculations for me? If I use 50 years return period, and I tell you that it is 10 meters per second, can you tell me how to get the 100-year return period estimation and the estimation for 200 period? 200 years period, or even longer, 500 years period. I can give you 3 minutes, okay? So by your calculations, I think you can have a curve if you connect them together like this, right? So, like that. So it means if we have a design with more years return period criteria, we will have a safer design, right? Because you assume that we have a greater wind speed, and you should leave more margin for that. It means your structure is safer, or your design is safer, right? About the other estimation, if after you have the wind speed in 100-year return period, and we use that as a reference value, the reference value for the head is 10 meters. I tell you that it's 10 meters. Can you calculate the wind speed at different heads? If you do this calculation, I'm sure you will have something again like that. If here is U, here is Z, right? And you will find that after probably 50 meters or 100 meters, they will be same. And we have a maximum value like here, like a wall. Okay?
What's the alpha there? This one, in the equations. Alpha.
It's a constant given by this table.
Okay.
And you always have a table like this from somewhere.
So
Okay?
we will take just in 1 hour, yeah? If you, for example, want to calculate the heat.
Yeah, you see? In
Yeah.
this case, it's 1 hour, so you use the two constants here.
Okay.
Yeah?
Please, can you go to the next slide, please?
Sorry?
Next slide, sir, please. Sorry. The Q100, what does it mean? Does it mean the mean wind speed?
With 100-year return period. Yeah.
So we are always using 100 for this one, eh? Or we can change.
It's a practice. You don't always use that. It's a practice.
No.
Okay? Okay. Steady and dynamic wind loads on your structure. So, as we know, from wind we have two parts acting on this structure. If we know average wind speed and we don't have very specific requirements for your calculation, we can just estimate the pressure. Okay? And for this case, we assume that we have a stable wind speed and it's U something or U0. Okay? And here is the axis for time. You just record the wind speed. It doesn't change. And actually we can have this from our laboratory. Oh, I use another symbol. U average. Okay, it's better. So, in this case, we can use a very traditional or classical estimation even when we were very young. Probably we know how to do the estimation because we need the factor of air density, right? And to different things, we should have different drag coefficients. And of course, you need to know the phase area. And we just use capital A. And the most important thing is the wind speed. And it's a parabolic curve. Here is a very classical one. But when we use this equation from different criteria or from different shear resistor societies, maybe the requirements are different or the criteria provided by them are different, quite different. For air. For example, this table is from, well, it's from Professor Longin again, but he got this from API, American Petroleum Institute. Thank you. And they have some definitions for the coefficients, but the coefficients could be different for different structures, for different things. And another thing is, when you use this equation, when you use this estimation, probably it's not just in this way, it's not so simple. For example, oh sorry, here is the example. Another point here. This one is applied by API, but by the estimation from DNV, we have another one. The form is quite similar, but when we use the calculation, we have another constant according to DNV's criteria. We call this as shielding coefficients, because if your wind is coming from this way and your wind is flow over this pillar, it will act on this pillar again, right? If they are quite close to each other, you may have the vortex. So they use another constant to calculate this effect. But again, it's based on some experiments. Sometimes when you look at the equations like this, it doesn't make sense. It's just from some experiments. And according to the criteria, we just need to know where to go and where to check and how to use according to their requirements. Okay? And according to the criteria provided by DNV, they also have, oh sorry, it's here, another coefficient, is theta. When we define theta, it's a ratio, you can see that, it's a ratio between the real areas. For example, if we use this one as a case, and the show that. The wind is from this way, and we look at the two pillars from sky. The wind is from here, right? And the diameter is here, is capital D, and the height is h. It means if the flow is from here, the acting area should be D multiplied by H, right? the rectangular, the projection. And we have two pillars. In this case, it will be 2D and H, the real areas. But to this structure, we have another thing. The area enclosed by the outline, right? And if we know the distance between the two pillars, we know that the area will be D plus S. So here is the ratio, and the ratio is theta. Theta can be used in this estimation. But if you look at this case carefully, you can see that it doesn't make sense, because A is here, theta is here. The product of them again will be 2dh, right? Just the area. But because this case is quite simple, but imagine that you have a big structure with many components. This one is important, okay? If we go back to the API criteria, we see that we have a table for different constants, and we have a very simple estimation here enclosed by this red box. But here is the problem. They have a very strange criteria for the calculation. So if we look at this case, I have a wind from this way, and the wind speed is 50 meters per second. And all the members of the platform, I mean the area of the things like platform, like the deck tower, the platform here and the deck tower, the facing area to the wind is 100 square meters. So we have 100 square meters here. And the side face of them, this side and this side, is 40 square meters. But as we know, according to this definition, we don't need this one, right? We don't need the side surface. But actually, in their criteria, we do need this area, because they need to calculate the, sorry, not to calculate, they need to count in the friction of that wind to this face. So, again, another problem is because they have different features. For example, for this structure, you can see that it's a porous one. Wind can just go through. And for this structure, again, it's a porous one. Wind can just go through. But for this deck house, of course not. Otherwise, you can't stay in that house for accommodation. So usually, they calculate in different ways. So we should know exactly what is the face areas for that deck house, and in this case, the facing area, this face is 20 meters square. So you see, we have 3 different areas, and we have only one equation. So according to the criteria provided by API, we calculate in this way. For platform and the deck tower, we consider all the faces for calculation. The forward face and the side face. And if you look at them carefully, you can see that we calculate twice because it's porous. After this pillar, the wind will act on the other one behind that. Yeah. they count in the factors twice. So that's why you have a value 280 meters square in this case, just in this case. It's from here. And if you go back to the table, for overall projected area of the platform, we use CD as 1, right? So you know the area here, you know the constant here, and of course we know the density of air is 1.2, roughly 1.29 or 1.23 kilogram per cubic meter, right? And you know the wind speed. Of course, you can calculate the pressure on this structure. But please remember that we also have a deck horse on the platform, and we use another criteria. We use the constant as 1.5, and this time we calculate the area just one time, and we still use this classical estimation. So after this lecture, you can go through the calculation, and you can find that the pressure estimated by API is about 500 kilonewton. Okay, so we make a note here. To the exactly same thing, from API, the estimation is 475 kN. But according to a criteria from ABS, American Bureau of Shipping or Ship, they have a bit different equation.
So you have separated this?
Yeah, they calculate the things separately, and they have one more coefficient. But this style is quite similar. A half, and the air density, they have a coefficient for height, coefficient for shape, and area, and velocity square. And they give another table for different things. And in this case, for the exactly same thing, we use 3 of them: back horse, the platform, and the structures. So obviously, we will have a different result. So if you go through the calculation according to ABS, you see that the results are quite different, nearly doubled. Oh, sorry, 1.5, roughly, yeah. 1.5 times, right? So to a design, obviously, if we do the risk assessment based on this criteria, it will be much safer, right?
Which of the two criteria is more reliable?
It depends on your ship owner. Because if you design something according to this criteria, you need to give stronger structures. It means cost. Yeah.
It will depend on the risk assessment.
Just regarding the reliability, of course, this one is better. Is that to? Is that okay to carry on? A tricky part. talk about something related to shape. Related to wind spectrum. Because if for the previous case, of course, you can calculate the pressure or estimate the pressure by your handwriting. It's quite simple, as long as you know where to use the constants. But when you estimate the loading from this part, I really don't think you can calculate by your hand. That's because we need some theoretical things. But anyway, we can start from here. And today we do the estimations for this part by computers, by some software like maybe Aviva, but I'm sure we can do that by system. So in this lecture, you just need to know the theoretical basis roughly. If you know roughly, that's enough. So, in real world, if we have a tower like this and we send a guy over there and you just monitor the wind speed, I'm sure your signal will be like this, right? It's the real wind speed, and we use U, okay? So it's always fluctuating. But if your feeling is not very sensitive, you may think it's a stable wind and the value is like this, like the red line. But the truth is, it's a combination of stable wind and a combination of stable wind and fluctuation. And the fluctuation is like this. Or, no, it's better to draw here. If you put them together, it's the wind in real world. And when we do the pressure estimation, it's for this one. So to most cases in your principal design or your primary design, we call that primary design, right? This part is enough because this part is not quite big compared to this one, because it's always fluctuate around 0. It could be positive, it could be negative. So this part is important. But to some big wind or the wind in open sea, probably the fluctuation is big. So in some cases, we need to know the force or the load from fluctuation. And from this picture, we can see that when you feel the wind speed is roughly in this area is about 10 knots. Actually, you have some other winds with different speeds, like the fluctuations. So that's why we have something like wind spectrum to specify the wind signal, like this one. Okay? And for the function, because we always need a model to present the signal like this. So for the functions, we have different models. And something provided by API again, proposed by Davenport, or for something else, we also have a model from DNV, a model from ABS, and in China we have a model from CCS. So, but before all of them, we need to know what's that. So, to understand the spectrum, we need to know something about Fourier series. Am I right?
Yeah.
Say what?
Fourier transfer. And you can see that when we record something in real world, it's always go with time. And we say that it's in time domain. But if we want to use a model for that, of course, it's not okay to present this in time domain because it's a mess. So we do that in frequency domain. And we use Fourier transfer to transfer the signal in time domain to frequency domain. And for this frequency domain, we can have a model to present this function. They are the models we can use. Okay. So, why we can make the transfer between the two different things? Because they are completely different. Here is in real world, here is in mathematics. So I can show you some photos from a Chinese website. For example, in a very simple case, the first curve, can you see that? The black one, can you see the color? I can't see the color here. You can see a very strange curve here in black color. We can assume that it's a signal here, okay, just in this case. But the truth is we can use a combination of some very regular functions, or more specifically, we use a function like this, or many curves like this, combine them together, put them together, and have this signal, the nice one. Or, in a better case, you can see this messy curve, but again, it can be divided into many things like this, and to each of them, of course, you can give a function in this way, and it's very easy to present this, right? So we can say that the curve in real case is the combination of them, right? Maybe many of them, and m is a great value. But anyway, we can have a combination. We always have a combination like this, and real signal. And even this one have two angles here. We still have a combination of some regular signal. Put them together, have this strange one. So to any signals in real world, we can always have a combination like this. Okay? So now we nearly solved the problem. If you look at this one in time domain, it's really messy. But if we go to mathematics, we may have a trend or a function. If you still don't understand, I can show you something from Wikipedia. I think it's very, very good to understand how to transform them. See? We probably it's because of the lights. We can see it again. We can divide this signal into many signals like that. No, it's still not good, but roughly you can see that, right? And to the signals here, of course, we can use some functions, and we can analyze the signals in a mathematical way. So that's why we have some functions like the in this slide here. We can use different models for this. I give you a coordinate system here, and the first one, the axis is for the signal or the wind fluctuation in time domain. And according to Fourier transfer, we know that we can divide the signals into different regular signals. And all of them can be presented by equation like this, or by an expression like this. Okay, you can see that we need amplitude. We have a signal here, a regular signal, and we have the average wind speed. So after this presentation, you can see that we can feel this wind speed. And in the meantime, we still have the fluctuation here. And this fluctuation can be presented in this way, a combination of different signals. So if you just look at here, we have an amplitude. Based on this one, we have the amplitude of fluctuations of different signals. For example, if you look at this signal from this way, probably the amplitude is here. If you look at it in this way, maybe it's here. I mean the absolute values, right? If I give the signals a sequence from great values to small values, and I connect them, I will have a curve, right? And I can use a function to present this curve, because this is the axis for frequency because we use a frequency domain to divide the signal, right? So that's why you can see the models in this way. Therefore, SF for this curve. And the variable is f because for this curve, if I turn it around, it's f, it's SF, right? And you connect different things with a curve. We want to use a mathematical way to present this curve. And we can use some models like that, okay? In most of these models, we need frequency. We need, because it's some points here. And we need the average wind speed because we need to know how big of the base is, right? So, we may have more than 10 models from different countries and different classification societies, but well, it's up to you, or it's up to your ship owner. And that's the reason why when you go to CSAM, I mean the software for wind modeling, you can see some terms like this, because it's asking you to select at least one of them to present this fluctuation, and then by your computer you can calculate the force on that. But please remember, again, it's just a part of the wind force, because the wind force is always the pressure plus the fluctuation, and here it's just for the fluctuation. Okay? So if we just look at this function, this curve, in most cases, because we have different models for SF, right? But by most of them, we will have a curve in this way. And we should know that the low frequency part is important to your structure. This part. So, by Fourier transformer, we have transformed the real-time signal to mathematical ways. And then, of course, we have built up the relationships between them by some functions like this, right? It means if we know SF, or where is my, yeah. Actually, here is F in a different way, right? If we know the F, we know the SF. Actually, we can present this wind speed in some way. And in a very simple case, it can be calculated like this. So as long as you know the function here, you know the velocity. If you do integration, you have the whole range for the wind, or for the wind force, okay? But I don't think you have to remember the expressions here, because it's nearly impossible. And today we calculate the fluctuation force by computer. If in your exam you need something like this, I will show you the expressions, okay? But if you can understand roughly why we have something like this, that's enough, okay? Yeah, like you can see from this slide provided by Professor Longbin. Again, we still use this classical expression, but now we focus on the fluctuation part. We still can use the similar way. And after we ignore the second order part, again, it's quite simple, right? So I think it's enough. You don't have to remember this. It's too long. But the theoretical basis, please try to understand, okay? We can build up the relationship between the signal in real world and the signal in mathematical world, okay? So I think I have finished. Thank you very much. Are you okay with my language?
Yeah, that's fine.
Just fine?
That's fine. Just.
Hello. Dr. Meng,
Yeah?
can you send me this lecture?
I will upload
please?
to your system.
Yeah, because I'm going to library now, but you have lessons, and maybe you'll send it to later. I mean, not to lose the time. To revise it. I mean, I don't want to lose the time. I just want to revise it now. It is possible. It's not hard for you. It's just lessons 4 hours.
You can always have something.
There is only one place, yeah, for USB.
Yes, of course.
Are you getting on your memory stick? All of them? Because it could be useful.
Yeah, I'm going to library because
I'll ask a question afterwards.
yeah.
So after Saturday we need to knuckle
Thanks.
down. Big
before.
time. Big
For
time.
Saturday.
Come Monday it's time for me.
Recollecting some of my 6 years, 10 years back terms and which came across.
You alright? Yeah. You good?
I don't know because I don't know exactly.
Boring.
Yeah, because I
You've got no excuse. What's your excuse? No excuse.
Edinburgh maybe. I will go to Edinburgh today or
Ah,
yeah,
okay.
for traveling. So
Yeah,
I
that's
don't know
good, yeah, that's
exactly. Maybe next time.
It's a nice city.
Yeah.
Are you
I've
getting
been
the
there.
megabus? Yeah, of course. Are you getting the megabus?
Megabooks. What's that?
Bus. The bus. Get the bus. It's very cheap.
Oh, very
It's
cheap.
about 2.5 hours on the bus. It's not too bad.
Yeah.
But I would recommend it, especially if you're doing if you want to go see cities like London and stuff. Yeah, it's long, but it's very cheap. So it's worth looking into.
So how many people will come tomorrow?
1, 2, 3, Helen, the other Kazakhstan, and then Jay. So yeah, I don't know what else. It just hopefully the majority of us. Because we are going to go. So this will be our one time before we have to local time. So we may as well just enjoy it.
I really want to go to the party and go to Edinburgh both. So actually, I didn't reserve my ticket. Yeah. So
Honestly, look into Megabus because it's so cheap. Yeah, don't do train.
Or you can go next week.
Yeah, I'll go next.
You're going to stay here for 1 year.
yeah.
There's no rush.
Okay, I should consider it again.
But don't leave it until winter because it'll just be really cold and rainy. Sir? Yeah. In terms of the actual equations that you've just presented today, like in terms of like exam conditions, which ones would we be expected to know?
I will let you know.
Okay, but just for like reference now, just so like obviously I can prepare myself. Because just rough guard rather than obviously.
Because when we do some jobs like this, we always have some criteria as reference. So if you ask me now, I really don't know which one you want to.
No, yeah, no. I just mean just like in general, like which one would you have expected us to know? Like.
I think API is the first one.
Yeah, the first one. Okay, so question 1. Okay, that's not a problem. Because the other ones is just.
Right.
When you consider every other lecture as well, it's like all in one go. It's a bit difficult.
But you always have references. So
Yeah,
it's
no,
not
that's
a
good
problem.
then. Yeah.
As long as
It's-
you know how to use the equations.
And what they mean. Yeah, that's no problem. Happy days. Which room are we in now?
George.
Done.
Thank you. Thank you very much.
Where this is near the bathroom.
Do you play football?
Yeah, we
I
played
think I
once
saw you
together.
before.
Yeah, we played once or twice together, yeah.
Shall we go?
Yeah.
Next.
Shall we go? Okay. Thank
See
you very
you,
much.
bye-bye.
See you.
we got? Can't be right. How do I get on to? Where did I go? Start again. Thank God for that. Hi, good morning.
And there's people in here. Sorry, on the app it said 101, so we're all stood outside the lecture hall 2 floors down. So
But you all know to come up now, do you
Yes.
think? Right.